The radar operator's voice cracks across the intercom. Bogeys inbound, bearing 090, range 12 miles. It's 0820 hours, January 5th, 1943, 30 miles northwest of Guadalcanal. The light cruiser USS Helena cuts through the Solomon Sea, returning from a bombardment mission against Japanese positions at Munda. Her crew is exhausted. They've been at battle stations for 6 hours. Lieutenant Red Cochrane commands the aft 5-inch battery. Through his director sight, he watches 4 black specks materialize against the morning haze. Aichi D3A, a dive bombers, Vals, slow, obsolete aircraft that shouldn't pose much threat to a modern cruiser bristling with anti-aircraft guns. But the Vals are accurate, and they're persistent, and American gunners have learned to respect them. Helena's forward batteries open fire first. 5-inch 38 caliber guns, throwing 54-pound shells at 2,600 feet per second. The shells arc upward, their time fuses set to detonate at predicted altitude. The fire control computer has calculated the intercept point based on target speed, bearing, and rate of climb. Standard doctrine. The same calculations American gunners have been making since the war began. The shells detonate. Black puffs of smoke bloom in empty sky. The Vals keep coming. One Val breaks formation, diving on the attached New Zealand cruiser Achilles. The bomb strikes home. Achilles staggers, smoke pouring from her superstructure. The remaining 3 Vals complete their runs and turn to flee, diving for the deck, weaving through the defensive fire. Cochrane tracks one retreating Val through his sight, range 4,500 yards and opening. The bomber is already past the danger zone, or should be. Standard procedure says, let it go. You've fired your shots, the plane survived, move on to the next target. Wasting ammunition on fleeing aircraft violates doctrine when you might need those shells for the next attack. But Cochrane's ammunition isn't standard. In the magazines below his mount, shell handlers are loading projectiles marked with red bands. Classified. Secret. The projectiles look identical to standard 5-inch ammunition on the outside. Same size, same weight, same ballistic characteristics. But the fuse screwed into the nose is different. Instead of a mechanical timer that detonates at a preset altitude, this fuse contains something impossible, something that shouldn't work but does. Cochrane gives the order. Batteries release, aft mount, target the trailing Val, fire when ready. His crew trains their guns on the fleeing aircraft. The fire control solution appears in the director. Range 4,200 yards. Target speed 210 knots. Bearing 115. The gunners match their pointers to the indicators and fire. 2 salvos. 6 shells. They watch the projectiles arc across the sky. The Val doesn't try to evade. The pilot assumes he's clear. American 5-inch. Guns are deadly accurate at close range, devastating at medium range. But at this distance, with a maneuvering target, the hit probability is nearly 0. Every Japanese pilot knows this. At 4,000 yards, you're safe. The first salvo detonates. Not where the fire control computer predicted. Not at the altitude the mechanical timer would have triggered. The shells explode precisely 70 feet from the Val's fuselage, close enough that the radar inside each fuse detects the metal airframe and closes the firing circuit. The Val disintegrates, wings fold. The fuselage tumbles into the sea, trailing smoke and burning fuel. Cochrane and his crew stare. No direct hit, no lucky shot, the shells simply knew. They sensed the target and detonated at exactly the right moment to ensure maximum lethality. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. On the bridge, Commander Deke Parsons watches through binoculars. He's a naval ordnance officer, not assigned to Helena's regular crew. He's here specifically to observe this moment. The first combat use of the VT fuse, the proximity fuse, the weapon that 3 years ago was considered impossible to build. Parsons picks up the radio. His message goes directly to Washington, to the Applied Physics Laboratory in Maryland, to Section T of the National Defense Research Committee. 3 words. It works. Repeat. It works. 3,000 miles away, in a laboratory building that didn't exist 2 years ago, a team of physicists and engineers receives the message. Some of them cry. Others just sit in silence, absorbing what it means. They've built something that will change naval warfare. They've solved a problem that everyone said couldn't be solved. They've fit a working radar set into a 5-inch artillery shell and made it survive forces that would crush a man instantly. And they did it because they had no choice. Because without this weapon, American ships were dying. 18 months earlier, August 1941. The conference room at the Naval Research Laboratory in Washington, D.C. is crowded with senior officers and civilian scientists. The meeting has been called to address a crisis that threatens to undermine American naval superiority before the United States even enters the war. Rear Admiral Harold Bowen presides. On the table before him lies a stack of reports from British naval operations in the Mediterranean and Atlantic. The data is grim. Modern aircraft are changing naval warfare in ways the admirals never anticipated. Gentlemen, Bowen begins, we have a fundamental problem with anti-aircraft defense. He gestures to a chart showing hit probabilities. Against a bomber flying at 200 knots at 12,000 feet, our 5-inch batteries achieve a hit rate of approximately 3%. 3 shells out of every 100 fired will hit the target. A murmur runs through the room. 3% sounds low, but it's actually considered acceptable given the difficulty of hitting a small, fast-moving target at altitude. Bowen continues, but that 3% assumes the target maintains constant altitude, constant speed, and constant bearing. The moment the pilot takes evasive action, our hit rate drops below 1%. He pauses. And torpedo bombers don't attack from altitude. They come in at wave-top level, at high speed, maneuvering constantly. Against those targets, our hit rate is 0.5%, 1 hit for every 200 rounds fired. The room falls silent. Everyone present understands what this means. A heavy cruiser carries approximately 3,000 rounds of 5-inch ammunition. In a sustained air attack, the ship might expend all of it and score 15 hits. Against a determined attack by 20 or 30 aircraft, the mathematics are catastrophic. The British have experienced this at Crete, Bowen says. They lost 3 cruisers and 6 destroyers to air attack in a single week. The ships fought magnificently. They fired thousands of rounds. They destroyed several dozen German aircraft. But they couldn't stop the attacks. The Luftwaffe simply overwhelmed them. He looks around the table. The Japanese have excellent naval aviation. Carrier-based bombers, torpedo planes, dive bombers. If we can't improve our anti-aircraft effectiveness, we will lose ships. Perhaps enough ships to lose the war. At the far end of the table, a civilian scientist raises his hand. Dr. Merle Tuve, age 40, physicist from the Carnegie Institution of Washington. He's been working on a different problem for the National Defense Research Committee, but Bowen specifically invited him to this meeting. Admiral, Tuve says, the problem isn't the guns. The 5-inch 38 is an excellent weapon. The problem is the fuse. Bowen nods. Explain. He's not a military man, never served, but he has the kind of practical intelligence that makes admirals listen. He draws a simple diagram. An aircraft, a shell trajectory, a detonation point. Current doctrine uses time fuses, Tuve explains. The fire control computer calculates time of flight to the predicted intercept point. The fuse is set mechanically before firing. The shell travels upward, the timer counts down, and at the predetermined moment, the fuse detonates the shell. He draws another diagram. The problem is prediction error. The fire control computer assumes the target will maintain course and speed, but pilots don't cooperate. They climb, dive, turn, accelerate. By the time the shell reaches the intercept point, the aircraft is somewhere else. The shell detonates in empty air. One of the naval officers speaks up. We understand this, Doctor. It's an inherent limitation of anti-aircraft fire. Unless we develop predictor, systems that can account for evasive maneuvers. Or, Fuze interrupts, we develop a fuse that doesn't require prediction. A fuse that senses the target and detonates automatically when it's close enough to do damage. The room erupts. Multiple officers speak at once. The concept isn't new. Proximity fuses have been discussed for years. The British are working on them. The Germans are supposedly researching them. But everyone agrees they're impossible to build. The technical challenges are insurmountable. Fuze waits for the room to quiet. I know what you're thinking. A proximity fuse requires electronics, radio or optical sensors, power supplies, circuitry. All of it has to fit inside a 5-inch projectile, survive being fired from a gun, function reliably in combat conditions, and cost little enough to manufacture in quantity. He pauses. 6 months ago, I would have said it was impossible. And now? Bowen asks. Now I think we can do it. Fuze returns to the blackboard. The British have shared some preliminary work. They've built experimental fuses using miniature vacuum tubes. The tubes break when fired, but the concept is sound. Radio frequency oscillation, reflected signal detection, automatic detonation when the reflection reaches threshold intensity. It's essentially a miniature radar set. He writes specifications on the board. We need vacuum tubes that can survive 20,000 times the force of gravity. We need a power source compact enough to fit in the fuse cavity. We need an antenna that won't break off during flight. We need circuitry simple enough to manufacture, but sophisticated enough to discriminate between targets and false returns. An engineering officer shakes his head. Dr. Fuze, with respect, you're describing components that don't exist. The smallest vacuum tubes available are hearing aid tubes, and they're fragile. They shatter if you drop them. You're proposing to shoot them out of a cannon at 2,600 feet per second. I know, Fuze says. That's why I need 6 months and a blank check. Bowen studies him. What's your confidence level? 50-50, Fuze admits. Maybe we succeed. Maybe we fail. But if we don't try, we lose ships. Guaranteed. The Admiral makes his decision. You have your 6 months. And your budget. Set up a development section. Bring in whoever you need. Military priority alpha. Whatever resources you require. He stands. Gentlemen, this is now the Navy's highest priority ordnance development program. Second only to radar itself. Fuze leaves the meeting with his authorization papers. He has 6 months to build something impossible. 6 months to miniaturize electronics that barely exist. 6 months to solve engineering problems that violate basic physics. He makes a list of people he needs. Physicists, electrical engineers, mechanical engineers, radio experts, glassblowers for vacuum tube production, mathematicians to model the radar equations, chemists to develop new materials. The first name on his list, James Van Allen, age 27, physicist from the University of Iowa, currently working at the Carnegie Institution. Van Allen has been experimenting with photoelectric detectors. He understands circuits, he understands instrumentation, and he has the kind of creative stubbornness that refuses to accept impossible. Fuze calls him into his office. Jim, I need you to design a vacuum tube that can survive being shot out of a 5-inch gun. Van Allen blinks. That's impossible. I know, Fuze says. Do it anyway. Van Allen goes to work. He starts with commercial hearing aid tubes manufactured by Raytheon and Sylvania. Miniature triodes, about 1¼ inches long, 3/8 inch diameter, glass envelope, internal filament, fragile as crystal. He mounts one in a block of concrete and drops it from 10 feet. The tube shatters. He tries again with padding. The tube shatters. He tries spring mounting. The tube shatters. After 2 weeks of failed drop tests, Van Allen realizes the problem. It's not impact force, it's acceleration. A 5-inch gun accelerates the shell from 0 to 2,600 feet per second in the length of the barrel. That's 0.008 seconds. 20,000 times the force of gravity. The tube doesn't shatter from hitting the breech. It shatters from the initial acceleration spike. He needs a tube that can withstand forces no vacuum tube has ever experienced. The filament can't break, the glass can't crack, the internal elements can't shift. Van Allen contacts Sylvania's engineering department. He explains what he needs. The engineers are skeptical but intrigued. They start experimenting with thicker glass, different filament materials, improved mounting techniques. Meanwhile, Van Allen works on the circuit design. The basic concept is simple. A radio oscillator transmits a signal. When the signal reflects off a target and returns to the receiver, the combined, transmitted and reflected signals create a beat frequency. When that beat frequency reaches a certain threshold, indicating the target is close enough, a firing circuit closes and detonates the shell. Simple in theory, nightmarishly complex in practice. The oscillator has to operate at about 70 MHz. The receiver has to be sensitive enough to detect weak reflections, but not so sensitive it triggers prematurely. The power supply has to provide stable voltage, despite the spin and vibration of the shell in flight. The antenna has to radiate efficiently without breaking off, and all of it has to fit in a space smaller than a pint milk bottle. Van Allen builds breadboard prototypes on his laboratory bench. He tests each component individually. The oscillator works. The receiver works. The firing circuit works. Then he tries to integrate them, and everything fails. The circuits interfere with each other. The oscillator frequency drifts. The receiver picks up false signals. He works 16-hour days. His laboratory becomes a maze of test equipment, circuit diagrams, and prototype components. He fills notebooks with equations, sketches, troubleshooting notes. One breakthrough comes from Lloyd Berkner, another Section T researcher. Berkner proposes using separate tubes for the transmitter and receiver instead of a combined autodyne circuit. This reduces interference and improves reliability. Van Allen incorporates the change. The performance improves markedly. Another breakthrough comes from the power supply team. Conventional batteries won't work. They're too large, and they drain during storage. The team develops a unique solution. A reserve battery that activates on firing. The battery consists of stacked plates surrounding a glass ampule containing electrolyte. When the shell fires, the acceleration breaks the ampule. The spinning motion distributes the electrolyte across the plates. The battery activates and provides power for approximately 60 seconds, long enough for any realistic engagement. By December 1941, Van Allen has functional prototypes. The tubes survive drop tests. The circuits work on the bench. Now comes the real test, firing them from an actual gun. The Naval Proving Ground at Dahlgren, Virginia, January 1942. Van Allen and the Section T team have brought 50 prototype fuses for live-fire testing. The fuses are loaded into 5-inch projectiles, carefully checked, and handed to the gunnery crews. The first shot fires. The shell arcs downrange. The telemetry team watches their instruments. The fuse has activated. The oscillator is functioning. Then, 3 seconds after firing, the signal dies. Premature detonation. The fuse exploded the shell thousands of yards short of the target. They fire again. Same result. Premature detonation. And again. And again. Out of 50 fuses, 47 detonate prematurely. The remaining 3 fail to detonate at all. Van Allen examines the telemetry data. The problem is clear: microphonic noise. The oscillator tube they're using has 2 filaments. As the shell spins, the filaments vibrate at slightly different frequencies. The vibrations create audio frequency noise that the amplifier interprets as a return signal. The fuse thinks it's detected a target and detonates. Back to the drawing board. Van Allen redesigns the oscillator tube with a single filament. Sylvania manufactures new tubes. More testing at Dahlgren. More failures. Glass breakage. Circuit malfunctions. Battery failures. The 6 months are up. They're nowhere close to success. Fuze goes back to Admiral Bowen. We need more time. How much time? Another year. Maybe more. Bowen looks at casualty reports from Pearl Harbor. The Japanese attack happened while they were testing. The Navy lost battleships to aircraft. The proving ground, Fuze predicted. You have your year, Bowen says. But understand, every month we don't have this weapon costs us a cruiser. Every 3 months, a battleship. Make it work. 1942 becomes a year of relentless iteration. Van Allen and his team test hundreds of tube configurations. They modify glass formulations. They experiment with different filament materials. They redesign mounting systems. Every failure teaches them something. Every success reveals another problem. By spring of 1942, the work has outgrown the Carnegie Institution's facilities. The Navy establishes a new laboratory specifically for proximity fuse development, the Applied Physics Laboratory at Johns Hopkins University, located in Silver Spring, Maryland. Merle Fuze becomes the first director. The staff grows from 100 researchers to over 800 within months. The laboratory operates under wartime secrecy protocols, exceeded only by the Manhattan Project. Workers sign security oaths, armed guards patrol the perimeter, mail is censored, employees can't tell their families what they're working on. The fuse is given a deliberately misleading name, Variable Time Fuse, or VT fuse. Anyone asking questions is told it's a new type of timer mechanism. Nothing about radio. Nothing about proximity detection. Sylvania Corporation becomes the primary vacuum tube supplier. Their engineers work in parallel with Van Allen's team, each improvement feeding back into the design. They discover that thicker glass helps but makes the tubes heavier. Lighter filaments survive better but produce weaker signals. Every parameter is a compromise. By summer, they achieve 52% reliability in test firings. 52%. Barely half the fuses work correctly. In conventional warfare, this would be unacceptable. But Admiral Bowen makes a calculated decision. 52% of something revolutionary is better than 100% of what they already have. He authorizes production. The Crosley Corporation receives the first manufacturing contract. Crosley normally builds radios and appliances. Now they're building precision military electronics. The contract calls for 5,000 fuses, delivery by year's end. The engineering challenge is immense. Each fuse contains 130 miniaturized components, 5 vacuum tubes, precision resistors, capacitors, the reserve battery, the antenna, the firing circuit, all of it assembled by hand with tolerances measured in thousandths of an inch. Lewis Clement, Crosley's vice president of engineering, later recalls the pressure. We were told this was the Navy's highest priority. Every fuse that failed in combat meant American sailors died. We worked around the clock. 3 shifts, 7 days a week. Quality control inspectors rejected entire production runs for minor defects. We didn't argue. We built them again. Production begins slowly. By September 1942, Crosley delivers the first batch of fuses that pass Navy acceptance testing. 500 units. They're loaded into projectiles, packed in temperature-controlled crates, and shipped to Mare Island Naval Shipyard near San Francisco. Commander Deke Parsons, the naval ordnance officer who witnessed the fuse's development from the beginning, receives orders to escort the first combat shipment to the Pacific. He's also ordered to select ships for initial deployment and train their gunnery officers. Parsons consults with Admiral William Halsey, commander of South Pacific Forces. Which ships are most likely to face air attack? Halsey's answer is immediate. The carrier task forces, the cruiser Helena operating in the Solomons, the carriers Enterprise and Saratoga. In November 1942, Parsons boards Helena at Noumea in New Caledonia. He brings 3,000 VT-fused projectiles, carefully counted and logged. He assembles Helena's gunnery officers in the wardroom and explains what they're about to receive. Gentlemen, these shells contain a proximity fuse that will revolutionize anti-aircraft fire. The fuse uses radio waves to detect targets and detonate automatically at optimal range. You don't need to set time fuses. You don't need to predict target altitude. Point your guns, fire, and the shells do the rest. The officers are skeptical. They've been promised miracle weapons before. Most didn't work. Lieutenant Red Cochrane, commanding the aft 5-inch battery, asks the obvious question. What's the catch? Parsons doesn't sugarcoat it. Reliability is around 60%. 4 out of 10 rounds might not function correctly. Some will be duds. Some might detonate prematurely. But the ones that work will be 3 to 4 times more effective than conventional time fuses. 3 to 4 times? Another officer asks. How is that possible? Parsons shows them the mathematics. A conventional time fuse creates a lethal fragment zone, approximately 60 feet in diameter at detonation. If the aircraft isn't within that 60-foot sphere, the shell is wasted. The proximity fuse senses the target up to 70 feet away and detonates automatically. It effectively makes the target 50 times larger from a probability standpoint. The shell doesn't have to hit the aircraft, it just has to pass within effective range. He concludes his briefing with a warning. These fuses are top secret. If a dud lands on a Japanese-held island, it must be destroyed. Under no circumstances can the enemy recover an intact fuse. If they learn how it works, they might develop countermeasures or build their own version. Over the next 6 weeks, Helena operates in the Solomon Islands, bombarding Japanese positions, escorting convoys, patrolling for enemy submarines. Her crew loads the VT-fused ammunition but doesn't fire it. No air attacks materialize. The special ammunition sits in the magazines, waiting. Then comes January 5th, 1943, the morning bombardment of Munda, 4 Japanese Vals, the attack on Achilles, and Lieutenant Cochrane's decision to fire at a retreating bomber at 4,200 yards. The kill is clean, undeniable. The gunnery radar tracks the shell bursts. The shells detonate within 70 feet of the target. The Val disintegrates. No lucky shot. No coincidence. The fuse works exactly as designed. Parsons sends his 3-word message to Washington. Then he requests permission to issue VT-fused ammunition to other ships in the task force. Within days, Enterprise and Saratoga receive their allocations. Within weeks, every major combatant in the South Pacific has VT fuses. The combat reports start flowing back to the Applied Physics Laboratory. Helena's next air attack. 5 salvos fired, 3 aircraft destroyed. Enterprise's engagement off Rennell Island. 8 salvos, 4 kills. The statistics exceed predictions. Gunners are achieving hit rates 4 to 5 times better than conventional ammunition. But problems emerge. The fuses have a shelf life. The reserve batteries degrade in tropical heat. Duds increase from 30% to 50% after 6 months of storage. Ships report that ammunition sitting in magazines through multiple combat deployments becomes unreliable. Van Allen, now commissioned as a lieutenant junior grade in the Naval Reserve, deploys to the Pacific specifically to address the battery problem. He arrives at Noumea in March 1943 and sets up a re-batterying station. Ships bring their old VT-fused ammunition. Van Allen's team carefully disassembles each fuse, removes the degraded battery, installs a fresh one, and reassembles the fuse. It's painstaking work. Each fuse takes 20 minutes to service. He establishes additional stations at Tulagi, Guadalcanal, Espiritu Santo, and Eniwetok. By mid-1944, the Navy has a logistics network specifically for maintaining VT-fused ammunition. Fresh batteries are airshipped to forward depots. Ships can exchange old ammunition for refurbished stocks. The dud rate drops back to acceptable levels. Meanwhile, production accelerates. Crosley is joined by RCA, Eastman Kodak, General Electric, McQueen Norris, and Sylvania. By the end of 1943, the factories are producing 40,000 fuses per day. By war's end, production will reach 70,000 per day. Over 22 million VT fuses will be manufactured at a total cost exceeding $1 billion in 1940s currency. The fuse's effectiveness becomes clear in the casualty statistics. In 1943, naval guns fire 36,370 anti-aircraft rounds in the Pacific. Only 25% use VT fuses, but those 25% account for 51% of all aircraft destroyed by gunfire. The ratio speaks for itself. VT-fused shells are 3 times more effective per round than conventional ammunition. Night engagements show even more dramatic improvements. Traditional time fuses rely on radar ranging to set detonation altitude. At night, radar accuracy degrades, gunners fire more shells and score fewer hits. VT fuses eliminate the ranging problem. The shells find their own targets. Night kill ratios increase by 370%. Rear Admiral Arleigh Burke, commanding destroyer squadrons in the Solomons, writes in his after-action report, "Mechanical time fuses were good for harassing enemy aircraft at night, but that was about all. The VT fuse changed everything. We started killing aircraft after dark. Japanese pilots who felt safe under darkness learned they weren't safe anywhere. By 1944, the strategic situation in the Pacific has shifted. American forces are advancing through the Marshall Islands toward the Marianas and Philippines. The Japanese, facing catastrophic pilot losses and fuel shortages, develop a desperate countermeasure: kamikaze attacks. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Traditional air attacks require trained pilots who drop their weapons and escape. Training takes years. Experienced pilots are irreplaceable. But kamikaze attacks require only enough training to fly the aircraft to the target. The plane itself becomes the weapon. Japan has thousands of aircraft stockpiled and tens of thousands of barely trained pilots. They can sustain kamikaze operations indefinitely. The first organized kamikaze attacks hit American ships off Leyte Gulf in October 1944. The results are devastating. Conventional air attacks achieved hit rates around 3%. Kamikazes hit ships 14% of the time. They're 4 times more effective than regular bombers. The reason is simple. Kamikaze pilots don't evade. They don't drop their weapons from altitude. They dive straight at their targets at maximum speed. This makes them easier to track but harder to stop. Fire control systems can predict their trajectory accurately, but the shells have to actually destroy the aircraft. Near misses don't work. A damaged kamikaze keeps coming. VT fuses prove ideal for kamikaze defense. The shell doesn't have to score a direct hit, it just has to pass close enough to detonate. The fragment pattern shreds engines, severs control surfaces, kills pilots. Even a heavily damaged kamikaze usually veers off course or breaks apart before impact. The statistics tell the story. Against conventional attacks, ships firing VT-fused ammunition expend approximately 1,800 rounds per aircraft destroyed. Against kamikazes, the expenditure drops to 500 rounds per kill. The simpler trajectory of suicide aircraft makes them easier to engage effectively. But 500 rounds per kill is still a staggering expenditure. During the Okinawa campaign, destroyers on radar picket duty face attacks by dozens of kamikazes simultaneously. They fire thousands of rounds in hours-long engagements. Some ships exhaust their ammunition and have to withdraw. Others stay on station and fight with whatever they have left. USS Helena, May 11, 1945. The destroyer is on radar picket station with USS Evans and 4 landing craft. At 0740 hours, radar detects a massive raid inbound, 156 Japanese aircraft, most of them kamikazes. The engagement lasts 90 minutes. Hadley's gunners fire continuously. 5-inch guns, 40mm Bofors, 20mm Oerlikons, every weapon on the ship in action. The VT fuses work as designed. Shell after shell detonates near incoming aircraft. Kamikazes disintegrate, veer off, crash into the sea. Hadley shoots down 12 aircraft before taking a hit. Then another. Then a third. Fires erupt across the ship. Casualties mount. But the guns keep firing. When Evans takes 4 hits and has to withdraw, Hadley stays on station. She shoots down a total of 23 aircraft before combat air patrol fighters arrive and drive off the remaining attackers. Hadley's crew fires over 3,000 rounds of 5-inch ammunition. Approximately 70% are VT fused. The after-action report credits the proximity fuses with enabling the ship's survival. Without VT ammunition, we would have been overwhelmed in the first 30 minutes. The fuses allowed us to engage multiple targets rapidly, without calculating individual time settings. We simply aimed and fired. The shells did the rest. Similar patterns repeat throughout the Okinawa campaign. Ships equipped with VT fuses survive attacks that would have sunk them with conventional ammunition. The casualty statistics are stark but clear. VT-fused shells require approximately 4 times fewer rounds per kill than time-fused shells against all target types. Japanese aircrew who survive kamikaze missions report that American anti-aircraft fire became uncannily accurate in late 1944. Shells that should have detonated too high or too low instead exploded precisely at aircraft altitude. Pilots diving through defensive fire found themselves flying into shell bursts regardless of evasive maneuvers. Some pilots reported that the Americans seemed able to predict their exact flight path. They weren't predicting. The shells were sensing. Japanese intelligence services never determined how American anti-aircraft effectiveness improved so dramatically. They captured several duds VT-fused shells that failed to detonate when they hit the ground. Japanese ordnance experts examined them but couldn't determine their operating principle. The fuse components were destroyed by impact. The critical vacuum tubes shattered. The circuits were unreadable. Germany faced the same mystery. When VT fuses were authorized for use over land during the defense of London against Vone flying bombs in June 1944, British anti-aircraft batteries began achieving kill rates of 79%. The Germans launched 9,300 V1s between June and August. By the end of August, British guns equipped with proximity fuses were destroying 4 out of 5 incoming missiles. German engineers recovered several intact fuses from duds. They analyzed the components. They identified the vacuum tubes, the battery, the antenna. But they couldn't reverse engineer the complete design before the war ended. German proximity fuse research, which had begun in the 1930s, never produced a working combat weapon. After the war, interrogations revealed that German military scientists had developed over 30 different proximity fuse concepts, radio-based designs similar to the American VT fuse, acoustic designs triggered by engine noise, electrostatic designs using capacitive effects. None reached production. The technical challenges proved insurmountable without the industrial base and resources that America brought to the problem. The VT fuse's impact extended beyond anti-aircraft use. In December 1944, General Dwight Eisenhower authorized use of proximity fuses for field artillery during the Battle of the Bulge. Artillery shells fused to detonate 20 to 50 feet above ground created devastating anti-personnel effects. Shrapnel rained down on troops in foxholes, trenches, and behind cover. German infantry caught in the open suffered catastrophic casualties. General George Patton wrote to the War Department, "The new shell with the funny fuse is devastating. We caught a German battalion trying to cross the Sauer River with a battalion concentration and killed by actual count 702. I think when all armies get this shell, we will have to devise some new method of warfare. I am glad you all thought of it first." Patton's assessment was accurate. The proximity fuse didn't just improve existing weapons, it changed the tactical calculus. Artillery became far more lethal. Anti-aircraft guns became far more effective. The defensive advantages shifted toward forces equipped with VT fuses. Secretary of the Navy James Forrestal later wrote, "The proximity fuse helped blaze the trail to Japan." He wasn't exaggerating. The fuse enabled American naval task forces to operate in range of Japanese land-based aviation. Carriers could approach enemy-held islands without being overwhelmed by air attacks. Amphibious assault forces could establish beachheads under intense kamikaze pressure. The statistics support Forrestal's claim. Between October 1944 and August 1945, American ships in the Pacific fired VT-fused ammunition at 278 Japanese aircraft. Analysis suggests that without VT fuses, only 46 of those aircraft would have been destroyed using conventional time fuses. The difference, 200 to 32 additional kills, represented thousands of American sailors' lives saved. The human cost of those additional kills is worth considering. Each aircraft destroyed before reaching its target meant one kamikaze that didn't hit a ship. Each kamikaze that didn't hit meant fewer casualties, less damage, ships that remained combat effective instead of withdrawing for repairs. USS Bunker Hill, May 11, 1945, same day as Hadley's battle. A kamikaze breaks through the carrier's defenses and crashes into the flight deck. The resulting fires kill 396 men and wound 264. The ship survives but is knocked out of action for the rest of the war. One aircraft, 660 casualties. Multiply that by the 232 additional kills enabled by VT fuses, and the impact becomes clear. Thousands of casualties prevented, dozens of ships saved. Combat effectiveness maintained throughout the final months of the war. The technology's broader implications weren't lost on military planners. If a miniature radar could fit inside an artillery shell, what else could be miniaturized? The VT Fuse project drove advances in electronics, materials science, and manufacturing that laid groundwork for post-war developments. James Van Allen, who spent nearly a year developing vacuum tubes rugged enough to survive gun launch, later applied those same techniques to instrument packages for high-altitude rockets. His shock-resistant tube designs, originally developed for artillery shells, enabled the scientific instruments that discovered the radiation belts surrounding Earth. The Van Allen belts, as they came to be known, were found using technology descended directly from the VT Fuse program. Merle Tuve returned to the Carnegie Institution after the war and transformed it into a leading center for nuclear physics and radio astronomy. The organizational methods he developed for Section T, bringing together physicists, engineers, and technicians to solve practical problems under deadline pressure, became the model for post-war research laboratories. The manufacturing expertise developed by Crosley, RCA, Sylvania, and other contractors translated directly to consumer electronics production. The techniques for mass-producing miniaturized vacuum tubes, precision resistors, and compact batteries became the foundation for post-war radio and television manufacturing. The industrial mobilization that produced 70,000 proximity fuses per day proved America could manufacture complex electronics at scale. But in January 1943, none of the long-term implications mattered. What mattered was that USS Helena had shot down a Japanese bomber at 4,200 yards without a direct hit. What mattered was that Red Cochrane's gunners were watching the VT fuses work exactly as the scientists had promised. Cochrane later wrote in his diary, "We'd been told these new fuses would change everything. I was skeptical. Every new weapon is supposed to change everything. But watching those shells detonate right next to the target, seeing the valve just come apart, I knew this was different. This was real." The technical specifications are worth reviewing. Each Mark 32 VT fuse measured 4.5 inches long and weighed approximately 1 pound. It contained 5 miniature vacuum tubes, 1 oscillator tube operating at 70 MHz, 1 receiver tube, 1 amplifier tube, and 2 thyrotron tubes for the firing circuit. The reserve battery activated on firing and provided power for 60 seconds. The antenna was a flat spiral printed on a phenolic disc at the nose of the fuse. Total component count, 130 parts, most of them smaller than a fingernail. The fuse operated on a simple principle. The oscillator transmitted a continuous radio signal. When the signal reflected off a metal object, an aircraft, the reflected signal combined with the transmitted signal to create a beat frequency. As the shell approached the target, the beat frequency increased due to the Doppler effect. When the beat frequency reached approximately 700 cycles per second, indicating the target was within lethal range, the thyrotron tubes closed the firing circuit and detonated the shell. The entire sequence from detection to detonation took approximately 0.003 seconds. The fuse made the decision faster than any human could react. It didn't miss because of human error. It didn't hesitate. It simply measured the distance to the target and exploded at the optimal moment. This automation was revolutionary. For the first time, American weapons contained decision-making electronics. The Fuze sensed its environment, processed information, and executed a programmed response without human intervention. It was, in a very real sense, one of the first autonomous weapons systems. The philosophical implications worried some observers. Was it appropriate to delegate kill decisions to machines? What if the Fuze malfunctioned and detonated near friendly aircraft? What if enemy forces developed methods to trigger premature detonations? These concerns were discussed at length within the Naval Ordnance Bureau. The consensus was pragmatic. The Fuze made better decisions than human gunners could make in the available time. The margin of error favored automation, and the risk of malfunction was acceptable given the alternative ships being sunk by aircraft because conventional fuses couldn't hit maneuvering targets. Admiral William Leahy, Chief of Staff to President Roosevelt, later wrote, "The proximity fuse removed the human element from one of the most critical decisions in naval combat. When to detonate an anti-aircraft shell, it replaced human judgment with physics." The shell didn't care about fear, fatigue, or inexperience. It simply detected metal at close range and exploded. That cold mechanical certainty saved thousands of American lives. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.